Last time I went through a process flow diagram describing some of the water management issues in a polymer electrolyte fuel cell. The goal today is to go through a spreadsheet calculation, try to solve some of the mass and energy balances for this flow sheet, and draw some conclusions about what some of the process ramifications are for having to keep the membrane well hydrated. Here is the spreadsheet for solving the flow sheet I talked about last time. Like the SOFC process simulator that we talked about with thermal integration, this has a similar structure. There's basically four main sections of the spreadsheet. One is the primary input and output variables, where we're specifying things like cell voltage, utilization, that kind of thing. A stream table of temperatures that tell us what the temperatures are or is solving for temperatures. A section with thermo data in it, in this case for hydrogen, oxygen, nitrogen, and water, including liquid water. And I've also added here parameters for Antoine's equation, because we also need to know the saturation pressure of H2O at different points in the process. Over here on the right, we have the summary of the process flow diagram, which I showed you last time. And then below that are a series of mass and energy balance sections, where we have columns for the molar flow rate, enthalpy, and product, and some of those for ins and outs in each unit that we're doing an energy or material balance around. If we look over here at the primary variables, we can choose cell voltage. The other is single pass utilization. That is the amount of hydrogen that's feeding into the fuel cell that's consumed before being recirculated. The third parameter here is the flow rate of hydrogen in stream 6, which is also the extent of reaction in the fuel cell. I'm assuming here that the overall utilization of the process is 1. So in other words, all the hydrogen that goes in ultimately gets consumed. And so the extent of reaction and also the fuel flow rate are those of the same thing. I've chosen this as our primary basis for the reaction. So this is on per mole of hydrogen that we feed into the process. Another parameter is the oxygen stoichiometry ratio, meaning how much excess air is being fed into stream 3 in order to consume the amount of hydrogen we're consuming. This allows us to have a little bit of excess air, and it prevents using up all the oxygen on the cathode side, which is normally not desirable. We also can specify the stack temperature, which we're assuming is uniform and is maintained by some kind of cooling water, where in this case we're putting in 40 degrees C cooling water, removing it at 80 degrees, and keeping everything at 80 degrees within the stack. At that temperature, we can calculate using Antoine's equation what the water humidity level is in any of the gases that reach saturation with H2O, and I'll come back to the consequences of that in a bit. Another parameter here is beta, which I described earlier. This has to do with the number of water molecules that are dragged across the polymer membrane with each proton from the anode to the cathode. And then the other last variable here we can play with is the cooling water temperature. So everything in blue, these are inputs to the calculation. Things that are in green, those are outputs of the calculation. And things that are red are quantities that we're solving for iteratively using goal-seek, as we did with the SOFC. So in terms of the order of calculation, the way I've set this up is to first consider a energy and material balance around the fuel cell stack itself. One of the assumptions we made last time is that streams 4 and streams 10 are leaving the fuel cell at 80 degrees C in a state of water saturation. So they're carrying a certain amount of water with them. At the same time, we're moving a certain amount of water across the membrane with the current due to beta, and we're also making water on the cathode side. And so that's what we have down here. So basically what we're doing is we're taking the extent of reaction, which is the amount of hydrogen we're consuming. Because of the utilization, we know how much hydrogen is going into the stack. We also know, because we know the air stoichiometry ratio, we know how much air is entering the stack. And so we can do a material balance on the oxygen, the nitrogen, and the hydrogen for streams 3, 4, 10, and 9. And then for water, what we're doing is we're saying that the streams 4 and 10, those are leaving in saturation. So if we know the molar flow rates of, for example, oxygen and nitrogen, then we can say that the quantity of H2O gas must be equal to that total flow rate of oxygen and nitrogen times the ratio of the saturation pressure divided by 1 minus that saturation pressure. So in other words, the total pressure has to add up to 1 atmosphere, and we're calculating the fraction of that 1 atmosphere of gas, which must be steam, in order to have a saturation pressure of 0.471 in this case, which we have at 80 degrees C. And that, just to verify that, over here we're taking the ratio of the H2O flow divided by the total flow in the stream, and indeed it's 0.471. So this is the amount of water that must be flowing in stream 4 in order to have a saturation pressure of 0.471 atmospheres. So similarly, in stream 10, we can do the same thing. We know the hydrogen flow rate. We can figure out what the water flow rate must be in order to have 47% water. So those two are known, and then the H2O unknown in streams 3 and 9, we can solve that by material balance. So for example, to figure out the amount of H2O that must be in stream 9, we can take the amount of H2O in stream 10 and add to it the amount of water that had to have been dragged across the PEFC as a result of the proton flux. So if we take the extent of reaction, multiply that by beta times 2, because there's 2 protons per hydrogen, that tells us the amount of water that we're pumping across the PEFC. And so we need to have provided that water in stream 9. And so if we look at here, we're taking the amount of water that leaves, we're adding to it the water that is transported across the membrane due to electroosmotic drag. Likewise, on the air side, the H2O in stream 4 has to be the H2O in stream 3 plus the amount of water that we either made at the cathode or which was dragged across the membrane. So taking the difference, we can calculate water that must have been in stream 3. We can look at streams 3 and look at streams 9 to see what the H2O saturation is at those conditions. And you can see they're both less than 0.471 atmospheres. In other words, both of these streams 3 and 9 have a lot of H2O in them, but they're not at the level of being saturated. So we're not going to crash out any liquid water in those streams, which is good. Okay, so once we're done with the material balance, the rest is energy balance. And so what I'm doing here is calculating the enthalpy for the oxygen, nitrogen, hydrogen, and water in all of these streams, and also the enthalpy of the cooling water, which is entering and exiting the PEFC, and adding all those together. And the other thing I'm subtracting here is the electrical work. We know the cell voltage, we know the extent of reaction, multiply that by 2F. We can calculate how much electrical work the fuel cell stack has to be producing. And then we're taking the difference, and we're driving that difference to 0 by adjusting the water flow rate. So we change the cooling water flow, and we adjust that up and down until this energy imbalance is obeyed. And that gives us the PEFC cooling water flux, which in this case would be 35.4 moles per second if we're using 40-degree cooling water. Okay, so having done that, we can then do a mass and energy balance on the combiner, where we're looking at the steam injector. So stream 13 is injecting steam into stream 8 to create stream 9. We just calculated how much water we had in stream 9. We know how much water we have in stream 10, which is also the amount of water in stream 8. And so that difference tells us how much steam we have to inject in stream 13. And then we can do an energy balance. And what I'm assuming here is that stream 9 is at 80 degrees C. Stream 13 is at 100 degrees C. And so what we're doing is we're iteratively adjusting the temperature of stream 8 until this energy balance is obeyed. And that tells us that we are going to have slightly less than 80 degrees in stream 8, about 345 Kelvin or 72 degrees. So it's about 8 degrees cooler because of the additional enthalpy that's coming in the form of the steam. And then we can do an energy balance over here at this combiner, 7, 8, and 9, to figure out what the temperature in stream 7 has to be. Next is a mass and energy balance on the air combiner, so where we're taking the steam injector, combining it with dry air to produce stream 3. Similar set of issues. We know the oxygen and nitrogen flows. We know the H2O flow because we calculated the amount of H2O that we need in stream 3 previously. So it can go through and do an energy balance and figure out what the temperature in stream 2 would have to be, which in this case is about 71 degrees. Finally, there's an energy balance on the condenser. Here we know the flow rate of H2O and O2 and N2 in stream 4. I'm assuming no liquid water in stream form, so just saturated H2O. And the question is, how much of this do we have to condense in order to produce liquid that is sufficient to recirculate to the 2 steam injectors without needing any additional water? So this is not always the case. Sometimes you might have access to water at all times, and so you don't have to worry so much about water recirculation. But for mobile transportation applications or applications where you have a fuel cell that's not readily connectable to a water supply, it's very beneficial to try to eliminate stream 11 and recirculate, use all water that's completely recirculated. So the question is, what does the saturation temperature need to be in streams 15 and 5 in order to achieve that level of knockout? And then what is the cooling water flow that we need to this condenser in order to get that exact right amount of water? So what's happening here is we're taking the total amount of steam that we have to generate. That is what we're requiring to be the liquid flow in stream 15. And then what we're doing is we're calculating the saturation pressure that's needed in stream 5 in order to achieve that amount of H2O leaving that balances the amount of H2O that's being recirculated. So once we know what the saturation pressure is, we can back calculate what the temperature is, and that's what this is. It's saying that the condenser has to operate at 67 degrees C in order to condense enough moisture that we don't have to add any liquid water to the process. Once we know that, we can do an energy balance on the condenser as well. And here we're taking all the sum of enthalpies in, sum of enthalpies out. We're driving that to zero by adjusting the cooling water flow to the condenser. And that's adjusted over here. So it looks like it's about 20 moles per second of water that's necessary to recirculate in this condenser in order to knock out enough water. The last question is how much power is needed for the gas preheaters and for this boiler where we're generating steam. And we can do that by energy balance because we know the flow rates in these three streams. We can calculate the enthalpy difference and determine how much electrical power is needed in each of those heaters. And it turns out to be quite a bit. 60 kilowatts in this case for the steam injector, and then we also have about 5 or 6 kilowatts that we need for the gas preheaters. So as a final step, we can go over here. We know how much power we're generating at the fuel cell. We can also look at how much power is being consumed in the three heaters and subtract that. And we get a net power out of 135 kilowatts that we're generating at the fuel cell. We're only getting a net of about 69 kilowatts when we're all done with heaters. And that's, we can also, based on that, calculate the higher heating value efficiency or the exergetic efficiency. And you can see that it is quite low when we consider all that. So why is this efficiency so low? I think you can sort of see some of the consequences of the water management issue. Since we have to humidify all of these gases, we have to generate a lot of steam in stream 12 to be able to do that. Because the saturation pressure is so high, we're talking about half an atmosphere basically, half of our gas is steam. It means that streams 10 and 4 are carrying enormous amounts of gaseous H2O, which has a very high enthalpy, but it's only at 80 degrees. So it's very, very hard to recover the thermal energy contained in that steam. The best we can do is condense some of the water, but there's still a lot leaving in stream 5. And there's not much we can do about that if we're maintaining very high humidity levels in the PEFC. So what that's telling us is that to run at higher temperatures where the saturation pressure is so high, we end up having a huge cost to boil the water in order to maintain that humidity. So that is a definite penalty to operating a PEFC at higher temperatures. Ideally, we'd like to operate at lower and lower temperatures, in part because we really want to drive down the amount of steam generation that we have to do. The higher the temperature of the PEFC, the more energy we're going to end up wasting in terms of the steam generation. And so that's one motivation for trying to lower the operating temperature of a PEM as low as possible in order to eliminate that steam issue. Another factor affecting the same thing is the O2 stoichiometry ratio. Here we're using a 20% excess of air. But for example, if we were to increase this amount, then the amount of air we're dragging through the process and is ultimately leaving in stream 4 and then stream 5, that is going to carry with it a lot more steam at the same saturation pressure. So there's a definite disincentive to using a lot of extra air because that's going to drag a lot of steam out with it and cost even more in terms of electrical power. Finally, there's the cell voltage. Cell voltage really determines how much electrical work we're getting for a certain amount of hydrogen that we feed. The higher that cell voltage is, the more efficient our original process is going to be, and the more electrical work we'll have to operate with. So again, just like with an SOFC, if we want higher efficiency, we want to drive that cell voltage as high as possible. That may incur a much higher cell area, but it means that the efficiency of our process will be greater as the cell voltage gets higher. As the cell voltage gets lower, we're getting less electrical power, we're generating more and more heat, but because that heat is generated at such a low temperature in this case, there's almost nothing we can do with it. So in general, with PEFCs, we want to be able to operate the cell as a high voltage as possible without incurring too much of a cost in terms of cell area.